Good morning, everyone. Everyone is signing in right now, so we are very happy to have you at our third UC Lodi Water Management Workshop. This will go on until about 11:45 a.m. and we will have a break at 10:10 a.m. We cannot see the attendees' videos, so don't worry about that if you are in your lounging clothes. We also can't hear you, but you can interact with us via the chat or questions box. And if you have technical difficulties with that, just call 209-367-4727, the commission phone number, and Gabriella can help you. Good morning, Dwight. I see you figured out the questions box. Thank you. And we do have a few handouts for you today. So in your handouts area, there is the agenda for today's meeting, as well as the agendas for the first two workshops in case you wanted to see what we covered before if you missed them. Those recordings for the first two workshops are available at lodigrowers.com under the Education tab, and then there's a Presentations, Videos, and Handouts page. We also have a handout from Daniele in the handout section that is kind of a nice overview of some of the topics we're talking about today. So feel free to check those out. We have a really great lineup of speakers, as you can see on your screen right now. And we're very excited to hear from them and introduce them very soon. So the topics we're going to be covering this morning are water testing, remote sensing, soil zoning and variable rate irrigation, climate change impacts, and tips for prevention and mitigation of heat damage in the vineyard. We have applied and were approved for 2.5 hours of nitrogen management plan CEUs. So when you registered, if you indicated that you needed those nitrogen management plan continuing education units, you will get a certificate following this webinar so that you can have that for your records and earn those hours. Okay, it looks like we have a lot of our attendees on, so we will officially get going here. My name is Stephanie Bolton, and I'm the Grower Research and Education Director with the Lodi Winegrape Commission. The Commission plans a lot of different grower meetings throughout the year on a variety of topics. Water management is one of them. Water management is also very important in our Lodi Rural Sustainable Wine Growing Program. We have a big certification this year. We have 63,000 acres enrolled in the program this year across California, in Washington State, and in Israel. And there's a whole water management chapter that is available also at lodigrowers.com. Anyone can take a peek at those farming practices in that chapter and see if they match up, they line up with some of the things you're doing in your vineyard if you're not already a Lodi Rules grower. And unfortunately, we have the bad news to say that John Shin is unable to join us because, as you know, with farming, emergencies come up. But we will still have our Q&A session, and Daniele is going to do a great introduction for us as soon as I pass it over to him. And so that means that I need help with more questions during the talk. So if you have a question for any speaker or on any topic related to water management, anything that you get thinking about during today's seminar, go ahead and ask those questions through the questions box, and they will come to me and I will pass them along to the speakers during the Q&A session. We have a lot of great experts here with us this morning, so make sure we use their time wisely by asking all those questions that you have. Okay, so thank you for joining us. My email is stephanie@lodiwine.com if you have any follow-up questions. And I'm going to pass it over to Dr. Daniele Zaccaria. Thank you.
Thank you. Good morning, everyone. My name is Daniele Zaccaria. I'm an agricultural water management specialist with the University of California Cooperative Extension, and I'm based at UC Davis campus. I have most of my work, research and extension work on permanent crops. And let me give you a little bit of background on why we put together this 3-session on water management for wine grape growers. So in February, Stephanie and John came with a request to do a little bit of educational activities for growers. And in February, we were not talking about drought yet, but so we put together a program to touch upon the different aspects water management at a different scale. And so I put together together with all these people involved here, I put together the program, we reviewed the program, and we decided that what were the most relevant topics to discuss for efficient water management in wine grapes. And we did the first session on March 11, which is recorded, and that was on gathering the basic information for grapevine water management. The second session, we did it on March 18, and the title was Following the Pathway of Efficient Irrigation for Grapevine. And this is the third session, and is basically on the topic of improving water management at various scale. And so we decided to touch upon various scales of water management, from the farm scale to the field scale, up to the district scale, and a little bit more on the regional level. And so we have very good speaker and presentation today. So without taking too much of a time, I will introduce the first speaker, who is May Colomber. May Colomber is the nut crop farm advisor in Fresno County. We decided to invite May because she has a lot of experience in soil-water relationship and soil-water management. And so May, I'll pass the floor to you so you can start your presentation.
Okay, can you guys hear me all right?
We can.
All right, wonderful. Okay, and you can see my screen?
Looks great.
Okay. Okay, so today the first subject that we're going to talk about is interpreting results from water tests for your micro irrigation system. And when we're talking about evaluating irrigation water quality, there's a lot of things that we need to consider. One would be the particulate content of the water, whether that's coming from surface water or the groundwater, what the particulate content is. That's going to be really important to consider. You know, if you're at the beginning of designing a vineyard, it's going to be very important for your irrigation system design. A typical drip emitter, you want the largest particulate that passes through to only be 1/10 the size of your emitter. And so you, in looking at the different size ranges of sand, silt, and clay, that tells you that if you have a really high sand content in your water source, that's going to be really important to filter out to prevent clogging. We're also going to be talking about organic contaminants, algae and bacteria. Different types of chemical precipitates that could exist in the water. And so this lime is a big one of concern, along with which lime, or also known as calcium carbonate, bicarbonates, is something that's often overlooked, both in regard to irrigation system clogging, and then as well as its relationship with some salinity issues that we may have, and then iron, manganese, sulfides, and then also considering what the effect of different injected fertilizers could have on clogging potential. And so, as I mentioned, as I'm sure everyone knows, there are two main sources of water. You can either get your water from surface or from groundwater, and both of these can have different sets of problems that can arise and can influence which factors that you may request actually for an evaluation when you collect a water sample to send to the lab. Particulate matter can appear in both surface waters and groundwater, and organic materials are generally thought to be more of a problem with surface water, but sometimes when we have the presence of certain chemicals or ions that precipitate in the water, that can create an environment for bacteria. And then groundwater can also be high in salt, so we'll touch on that. It might be a little bit of a review for some of the things I discussed in some of the last sessions. So quickly, just water sampling and analysis for groundwater. You want to make sure that you're going to run your pump for at least 15 minutes before you collect a sample. You're going to need at least a 1 liter volume sample and a clean container for your chemical constituent analyses. And you want to collect that sample very close to the well. I sometimes recommend if you're troubleshooting some problems, you may want to take a sample after the filters to figure out, you know, if we're having some problems with the filtration, and at the end of the lines. You want to deliver those samples to a lab as quickly as possible, and if that's not going to work, make sure to store it in a cooler or a refrigerator until you can deliver it to the lab. And I always mention, just make sure to avoid a hot pickup truck because a lot of those factors that you're analyzing could be very volatile, or there could be those biological contaminants that can change really rapidly with heat. So you want to get as representative of a sample as possible. And then also, I forgot to put it on here, but with a surface water sample, you may want to get a larger than a liter, maybe closer to a gallon. Okay, so this is a list of some of the water characteristics that need evaluation and the ranges of concern from slight to moderate to severe. And I'll be going over some of these individually. And it's good to look at all of these factors together to determine the correct approach to keep your system clear and functioning properly. And the understanding the concentration of some of these potential problems are going to be important to make estimations of what amendments that you might need to use to correct the problem and what rate. So it's really important that the treatment that you're selecting matches the type of problem that's occurring. So a lot of times when these lab reports come back, you know, it's a lot of numbers, takes a little bit of practice to get used to understanding what the values are that you're looking at. But something common that you'll need to become familiar to make a conversion is between mill equivalents per liter versus milligrams per liter. And there's a simple conversion that you can do. This is the mill equivalents per liter is preferred for making these calculations for when you're determining some of the treatments that you might need, because when it's reported in mill equivalents, the individual cations and anions, this measure accounts for the ionic strength relative to the other ions, whereas in milligrams per liter, it's more relative. Okay, so back to particulates I mentioned earlier. So when we're looking at what comes from that report, the suspended solids is going to be important attribute to consider, those numbers are in units of parts per million. And so if we're getting upwards of 50 to 100 and over 100 on the suspended solids counts, then we know that there could be an issue with the filters. If you're starting from the beginning with planning a vineyard, there's a variety of filters available. The selection is going to be based on the flow rate, the concentration of inorganic and organic materials in the water. And even with a good filtration system, some suspended particulate matter is small enough to pass through the filters and clog micro emitters. So it's important to do regular inspection and maintenance on your micro irrigation system. Okay, so the organic contaminants that I mentioned, algae typically occurs in surface water, and that will have a greenish sort of color. And then if you are coming across bacteria, that's going to have a white, gray, blackish, or reddish brown color, depending on you know what metals the bacteria is feeding on. So they grow in conditions with elevated organic matter. So the bacteria can actually feed on dead algae. When we have high levels of calcium bicarbonate, iron, manganese, or hydrogen sulfide. These are all good conditions for bacteria growth. And both bacteria and algae provide food for more slime organisms. So small particles of either algae or bacteria can pass through the filter and into the drip system. And so the number that will come back on your report is generally going to be a count per liter, and these would be the ranges of numbers. So if you're trying to troubleshoot some clogging issues, attention to these bacterial counts will be important. Okay, chemical precipitates, iron and manganese are the most common. They exist naturally in groundwater, and generally they don't become a problem until pumping oxidizes them and converts them to an insoluble form that can lead to scale or induce growth with microorganisms in the water. And then also elevated sulfides can also form highly insoluble precipitates. So these are those ranges, pretty similar between the iron, the manganese, and the sulfide in terms of the ranges that you're looking at. Okay, so here's just an example of a report that I worked with on a grower. We were trying to figure out some different issues he was having. He actually had two different types of acidification going on different wells, and one of the wells was having a lot of problems and the other one seemed to be fine. And this was an example where when we took a sample before the filters, everything looked fine, but then when taking some water samples after the filters and at the end lines, we started to see some differences in the values we were getting back in the water report in terms of these bacterial counts. And so again, the iron-rich water can lead to the formation of this iron bacteria. And what we discovered was that they had an old irrigation main line that was not made of PVC, but rather of iron. And so that point of acid injection was releasing that iron into the water, and they were ending up getting really high levels of bacterial counts in the water, which was causing a lot of clogging issues. And so these iron bacteria will occur in a wide pH range, and so we will talk about some of the treatments for this a little later. Okay, more on chemical precipitates. So in addition to the iron, the manganese, and the sulfides that I mentioned, lime precipitation is a really big one. Probably one of the biggest concerns, at least for the area of grape growing down where I am on the west side of the valley. So lime is naturally occurring, or it can be provided in calcium amendments. And understanding the pH, the level of bicarbonates and calcium levels are really important to assess the potential of the water to precipitate this. And high levels of bicarbonate will precipitate calcium as the soil dries on the surface. So this can cause problems not only in your irrigation system, but also in the soil. And so when we get into talking about salinity issues, this can be important because that bicarbonate's often overlooked, but bicarbonate will precipitate the existing calcium that you have in the water, and then it's going to allow it's going to increase the sodium content, which could potentially drive problems with infiltration in the soil. Another thing to consider with the lime is that during the heat of the summer, that increasing temperature and increased evaporation can increase the insolubility of lime, making it even more difficult to control. And so it's important to maintain a pH between 5 and 7 for our micro irrigation systems. And this slide is courtesy of Mark Batney. So this I came across this and thought that this was a really nice illustration of what the effects of alkaline water can be when used in a vineyard. This figure represents changing pH levels from the vine row where the vines are being irrigated out into the row middle, and it shows the changing pH from where the water is applied versus where the water is not. And so this shows that the pH changed in a decade-old vineyard when alkaline water was applied. And as I mentioned earlier, the high pH, it can limit the macro and micronutrient availability to your vines. And so it's important to choose the right amendments, probably acid or acidifying fertilizers to lower that pH. But we also want to use caution with the use of that, because at extreme levels of acidity, we can also induce toxicity and deficiencies. So you can, if you want to read more about that, you can find that on Mark's blog, on the link there. Okay, as far as injected fertilizers go, this is also another really important thing to consider, and often maybe overlooked. Mixing fertilizers is generally considered to not be a good idea, though I think it's can be fairly common, at least in tree crops. And so we recommend always using a jar test according to the manufacturer instructions before doing so. And it's important when selecting fertilizers to consider what those constituents that I mentioned in the irrigation water. Mainly, we're interested in what the bicarbonate levels are, the calcium, and the magnesium. And so when they exceed these levels of about 2 milliequivalents per liter, we have potential for clogging hazards, including precipitating lime. Gypsum can also precipitate so even though you're using gypsum, if there's large levels of calcium, residual calcium on the surface of the soil, and you don't flush all that gypsum through, it can still precipitate out and cause more problems than what you've solved. Because so calcium carbonate, magnesium carbonate, quartz silicate, clogging hazards in your irrigation system. Just a little aside about the source of nitrogen in irrigation water. It's important to, in regard to your nitrogen management planning, to have an idea of what the pounds of nitrogen that you're applying over the season. So if you have up to 10 parts per million in your soil and you apply 30 inches in a year, that could be, I believe, well more than what you would need for your vines in a given year. So too much nitrogen can lead to defoliation, excessive vigor, and reduced quality. So very important thing to consider on your water quality assessment. Okay, so just a few quick notes on clogging prevention. You want to make sure to do routine cleaning and maintenance to prevent those sand particles and biological contaminants from penetrating the system. You want to flush the main lines and your sub mains using flush valves, and open the lateral line ends to flush, maybe as often as every 2 weeks if necessary, maybe less if your system's running clean. And sometimes it's important to even manually flush your self-flushing lateral lines. You want to run your irrigation before and after fertilizer injection. So you want to make sure you run it before to make sure it's running at the right pressure for the injection, and then you want to make sure to run it afterwards to make sure that all of the fertilizer has been flushed from the system, so that we don't cause some of these fertilizer-induced clogging problems that I mentioned earlier. You want to do regular system irrigation inspection. Make sure you're looking for leaks, changes in pressure, and wetting patterns.
5 minutes.
Okay. So in terms of the slimy bacteria and algae, generally we recommend chlorine treatment with liquid or gas. If you're doing this at a continuous rate, that would be at about 0.5 to 1 ppm. And you can do it in larger doses if you're just doing it periodically. For the iron and manganese, Some people use aeration or settling ponds in reservoirs, or you can oxidize the iron and magnesium precipitates with chlorine to have them settle out before reaching the micro irrigation system. There's also chelation products that are available. And then if you have elevated levels of calcium, magnesium, and bicarbonate, and high pH or iron sulfides, generally we're going to go with acid to maintain our water between 5 and 7. Really important. I mean, a lot of times you will need to, especially when injecting chlorine, you need to control the pH. So it's going to be necessary to use both chlorine and acid, but you want to make sure you never directly mix the two together. So they need to be injected at 2 different ports, I think approximately about 10 feet apart. Quickly on salinity, we talked about this a little bit in the last session, but it's important in your water quality assessment to assess the levels of sodium and chloride and boron in your water. One, to look for potential for osmotic stress, and then at very high levels, this could cause specific ion toxicity, where you start to see some marginal necrosis or worse on your vines. It's important to look at the pH for assessing the potential for nutrient deficiencies, and then again the ratio of sodium to the electrical conductivity, important to determine if you have potential for infiltration problems, and looking at the SAR, the pH, the levels of bicarbonates are going to give you some idea of what the appropriate amendments are going to be. So again, the SAR to EC rate, when you have a higher level of sodium relative to the amount of calcium and magnesium in the soil, that's sort of the, in a nutshell, recipe for infiltration problems. So this is just telling you, okay, you want to look at the level of carbonates in your water and free lime in the soil to determine, should I use a sulfur-based product or should I use a calcium-based product? And so it's really important to make this distinction so that you're not enhancing your clogging problems by choosing the wrong amendment. After amending your water, you're likely in extreme situations like this to see a lot of precipitated lime on the margins of where your drip system is. So it's going to be important to flush the system after these applications. Otherwise, those remaining salts will precipitate, and you'll see them on the soil as it dries. So in summary, things to consider: particulates, organic contaminants, chemical precipitates, and the salinity levels in your water. Water clogging potential varies with surface and groundwater sources. If an analysis points to a clogging potential, it's easier to make those system design changes or maintenance procedures. It's important to make those design changes early, prior to planting. You want to perform routine monitoring and maintenance. And one thing that I didn't mention that I might say is that, in a drought year like this year, the canal levels can be a lot lower than they are in a typical year. And so, we tend to think of surface water as being much cleaner, lower in salts than groundwater. But in a drought year, it might be important to do that evaluation. You might be very surprised that the salt content and the pH level might be different than what you're used to in other years. So make sure you do that salinity evaluation. Okay, and that's all I have. Thank you.
Thank you so much, May. So next up, we've got Dr. Mark Battany, who's going to talk to us about challenges and opportunities for irrigation management using remote sensing techniques. And Mark is the advisor for UC San Luis Obispo and Santa Barbara counties. Thank you, Mark.
Thank you very much. And if my audio gets choppy, let me know and I'll shut off my video feed.
Will do.
Can you see my screen okay?
Everything looks great and we can hear you very well.
Very good. Okay. Let's see. Okay, so just some background on the satellites that we're using to get this data. Landsat 7 and 8, these are our two US satellites. Each of these satellites takes 16 days to cover the entire globe, and because they're staggered and when they pass over, we get one reading every 8 days from the satellites. These satellites measure both the NDVI and the thermal. I'll talk about both of these. It's important to understand the pixel size or the resolution of their measurements. So for these satellites, it's a 30 meter by 30 meter NDVI pixel and 100 meter by 100 meter thermal. Okay, Landsat 7 was launched in 1999 and Landsat 8 was launched in 2013. So the nice thing, these have been up in the sky for quite a while. So we have a lot of historical data from them. And that's actually one of the best tools we have is looking back on the historical data. I'll talk a bit more about that later. Now, the good thing is Landsat 9 is scheduled to be launched in September of this year, and that will essentially replace the older Landsat 7, and that will really add some valuable additional data to our suite of information. Now, the Sentinel-2A and 2B satellites, these are the European Space Agency satellites. They're a little different here. They take less time to pass around the globe, 10 days for each one of them. And because they're staggered as well, we get a measurement from them every 5 days. And so that's really nice to have now between the Sentinels and the Landsats. There's a lot of imagery that's becoming available for any spot on the planet. And the nice thing too about the Sentinels, they have a smaller pixel size for the NDVI, this 10 meters by 10 meter pixel size. And that allows us now to use some of this data to do visual analysis of patterns in fields. And I'll give you an example of that. Unfortunately, there is no thermal measurement on the Sentinels, so we're still using the Landsats for that reading. These are newer satellites. The 2A was launched in 2015 and 2B launched in 2017, so we can't go back as far in time to get data from them, but still we have multiple years now of available historic data from them, and going forward we'll have data from all of these satellites. So this image represents the pixels from the two different NDVI resolution levels, and I have them overlaid on a vineyard, which I hope you can see underneath there. It's a little dark, but there's a vineyard with multiple different blocks having very different conditions. And if you can see, the center block has suffered from a lot of vines dying back. So that's something that we might want to sample separately. So that left image, that shows you what the 30 meter by 30 meter NDVI pixels look like as far as their size in relationship to the vineyard here. So the thing to keep in mind when you're using data from this size of pixel, you have to be somewhat careful if you're applying it to small fields, because the coarseness of this measurement will induce edge effects in your measurement if you're trying to take measurements all the way up to the boundaries of your field. So if you look in the upper left portion of that image, you can see that the pixels which overlay a portion of the vineyard and also a portion of the dirt road will have a much lighter value or a lower vegetation index than the pixels which are wholly within the vineyard block. So that's a really important thing to keep in mind when we're using these larger pixels. Also, the center weak area does not show up as well with these larger pixels in this image. There's actually two reasons for that. One is that I had to go back further in time to get this larger pixel size. This is from 2015, this image. So at that point in time, the decline in the vines that you see here was not as far along. So it's actually showing us a condition before the rapid or the quick onset of this decline. Now the image on the right, that shows you what the 10 meter by 10 meter pixel size from the Sentinel satellites. And so as you can see, there's a lot more detail that you will get from these smaller pixels. And this was a later image from 2020. So now you can see that area of declining vines shows up quite easily with these images. And also notice the edge effects here. So there still is an edge effect where a pixel overlaps the vineyard and the road, but it's a much smaller portion of the image is affected by that. So again, always keep in mind that the pixel size from these satellites is always going to be one of their major limitations for applying the data. Now, the thermal measurements from the Landsat satellites, these are measured on even a larger pixel, so 100 meter by 100 meter area. So that's a 1 hectare or 2.4 acres. So I've just made up some pixels that represent that size and now overlaying them on these 10 meter pixels from the Sentinel NDVI. And you can then really see the issue that we could run into when we're trying to apply measurements from these thermal satellite readings to smaller fields. The size of this pixel was really geared towards large fields, imagine center pivots in dry areas of the world, something of that scale. If you're trying to apply this information to small wine grape fields, it's going to be really hard to make them fit within your area of measurement. So you'll have very significant edge effects from that. When this data, though, is provided to us, the pixel, these 100 meter by 100 meter pixels, are actually resampled into smaller 30 meter by 30 meter areas just to match the other data from the satellites, but they're really not improving the quality of the information because they're still starting with one single value for that large pixel. So again, just keep that in mind. The other big limitation with satellites, because they're up in outer space, basically above the cloud layer, anytime you have significant clouds in between that satellite and the ground surface, you're going to result in either limited data or no data at all for that pass. And California here, we're pretty blessed for much of the summer that we don't have issues with much cloud cover in the summer when our key data is being measured. But this is an example from last June, the period June 9th to June 16th, showing you some of the cloud cover that did occur, and that during that time you would not have had satellite data from that Landsat 8 satellite during that time. So again, it's usually not a big issue for us in our area, but it can be a factor at times. It's certainly a bigger factor in other parts of the world.
You don't remember? Oh.
And keep in mind too, especially with the NDVI measurements, that the conditions on the ground are going to greatly influence what those readings mean to us as far as how we can interpret them. So here's some different examples of vineyards. If you look at the top two pictures there, the one on the left with that clean tilled floor, the NDVI value that you get from the satellite data is only going to represent the grapevine foliage. So that is a very simple interpretation of that data. We know that that value is really just the grapes. The situation on the right, and that picture was taken on the same day as the one on the left, now you see a bit more complicated situation where not only do you have the beginnings of the grapevine foliage for the season, but you still have quite a bit of cover crop. So you're going to get a much higher value from the NDVI reading. It will be obvious to you that that's not just reading the grapes, but there is no way to separate out what is grape and what is cover crop. You just have one single value for that. So you will need to use your own knowledge of what is going on in the field in order to interpret that information. The situation on the lower left there, this is a later in the season, say late spring, early summer, where we have some weeds along the vine row. As long as those weeds are not exposed to the satellites here, they're really not going to have much influence on the reading at all. So that situation is not going to be won't lead to much of a change in the data. The situation on the lower right, where now you have significant weed pressure and clearly is going to be exposed to the satellites, that is going to influence the value, whether it's the NDVI or the thermal readings. So again, you'll just have to have a way to understand what is going on in the field to help you interpret that information. So there's two different approaches to estimate how much to irrigate. So NDVI based information, how do we use this information? Well, the satellite NDVI is used to calculate a crop coefficient. So a crop coefficient value specific to the field that you're looking at, and that can be measured with every single pass of the satellite where data is produced. So you get a very complete picture of what the crop coefficient is over the entire season. And then you multiply that crop coefficient by the reference evapotranspiration to estimate your water requirement. So this is a calculation that a lot of us have been presented many times. Many of you probably use this. The difference here is that you're getting a more accurate a value of the crop coefficient for your site. Now, one thing to keep in mind is that if we were to talk to Larry Williams about whether or not this satellite reading is a true crop coefficient, he would point out that traditionally a crop coefficient indicates a crop which is fully well watered, and so it has an amount of vegetative growth that has not been restricted by any water stress. Well, your field, you are probably applying deficit irrigation if you're growing wine grapes, and therefore you have less canopy growth than you would if it was 100% supplied with water. So what that means is that this thing, even though we call it a crop coefficient, Larry would argue that it really shouldn't be called that, even though it's still related to how much water the field is using. So that's something that I think I'll show you a way that we can kind of work around that. The thermal-based measure, here we're using one or more surface energy balance equations to calculate the evaporation loss from a field. So a very different approach than from the NDVI. I won't talk about this as much. This is a newer thing, and there's going to be some changes or some new features, new products coming on the market here soon that I think will be of great interest to everybody here to maybe be able to apply this information more. But again, they're two very different approaches to using the satellite data. So where do we get this data from? There's a variety of sources that you can get this data from. I mean, remember, these are public satellites making information available on websites, and either you directly access this data or you go through either a public or commercial provider who's essentially repackaging that data for you. So the NDVI-based information, my all-time favorite website here called Irrisat. It's a free website. They take data from both the Landsat and the Sentinel-2 satellites, and they're using this NDVI approach by calculating the crop coefficient. And what I really like about this website, it was really designed to be used by farmers. It's very practical. Yeah, of course, you have to learn a little bit to how to use it, but once you figure it out, it's a really very easy to use tool. And I would highly recommend you take a look at it, not only for irrigation, but just for understanding what's going on in your fields. The thermal-based irrigation information, the biggest change coming down the pike here is this OpenET website. I have the link there for you. This also will be free. It's not going to be available, however, until later this year. My guess is they're waiting until the Landsat 9 satellite is operational, because that will then increase the amount of thermal data that's available for these calculations. So that will be one of the key ones to look at here. There are commercial providers using the available thermal data now. One example is this IrriWatch company, and there's their website there if you want to take a look at that. And there may be others there that you also are aware of. So the Irrisat website, again, this NDVI-based approach, this was developed in Australia by John Hornbuckle and others here in collaboration with global partners like Google and NASA and the USGS. Really, it was a very large effort for many people. And as the name suggests, this was intended primarily as an irrigation management tool. That's its main purpose here. It converts the NDVI to the crop coefficient with that relationship that I show you at the bottom left there. So the actual difference in the numeric value between the NDVI and the KC is not large. It's just the KC is a little bit larger than the NDVI value. Maybe the charts, the two bar graphs on the right, maybe show that a bit more cleanly for you. So again, when I use the term KC coming from this website, I'm meaning NDVI and vice versa. It's just a vegetation index telling us how much vegetation is visible from the satellites. So here's an example of how we can use that website, the Irrisat website. What I've done here, I've outlined in a vineyard here. This is actually a table grape vineyard in the southern part of the San Joaquin Valley. So I set up a perimeter in this field. I designated that as one of my fields, and which is now that information is stored in their system because I created an account to use this website. And then there's a number of menu items there on the left, and I just clicked on the KC, and now what it does, it calculates the crop coefficient based on the NDVI at that period of time. And now because this image was taken in late April of this year, you can see the number is relatively low as compared to what it would be later in the season. What I really like about this is because you can set up as many fields as you want, and they will be retained in the system. And so every time if you want to go back and get newer data from a site, you can easily go to your list of fields, select that field, and get updated information from it.
5 minutes.
Okay. Another thing you can do here on this, you click on that, the website then brings up the information on the crop coefficient, that's the top chart, and then it does calculations for you to look at the ETC based on that crop coefficient and local reference evapotranspiration. So if you look at that top chart, I know it's kind of small. Actually, I think my next one, there we go. Let's zoom in on that top chart here. You can see how the KC value from January up until the end of March, early April is quite small, and then it increases rapidly with vine growth, reaches a very large value throughout the growing season, and then begins to decline. So a lot of information here, but if your goal is to get a usable crop coefficient value from your fields, here's a very easy approach to get that. You can also download the raw data from these charts if you want to do your own calculations with the information. Here's one thing that I think would be a really good approach to people. Because we have access now to, the historical data from these websites, meaning you can go back in time and get your crop coefficient values from 5 years ago, 6 years ago if you want. We can use that information to help understand what we've been doing in the past to then serve as a guide for what we can do going forward. So that top equation I show you, irrigation equals KC times ETO times a deficit factor. That's normally what we use to calculate irrigation amounts. If we just rearrange that, we can, if we have our historical applied irrigation and the crop coefficient from this website and the reference evapotranspiration, either from the website or from our own data, we can then solve for the deficit factor that we were using at that period of time. So let's say, for example, if you knew that in 2019 you had a really good year, you really did things just right, you want to duplicate that. If you do this calculation for what you did in 2019, you can figure out what deficit factor you applied. That then gives you a target for what you can now do in the future going forward. So I think it's a really neat approach to using the historic data. As long as you have records of how much irrigation you applied, you can do this. So if you don't have irrigation records, I highly recommend you start keeping them because it really opens up opportunities for you to do calculations in the future. The other thing we can do with this smaller pixel NDVI information that's coming from the Sentinel satellites is looking at patterns as they develop in the field. Okay, so these are maps of the crop coefficient, which again is basically the NDVI, and you can see things developing over time this last year. Now there's two streaks running across that field. Those are a road and a ditch. I just included them in this image, but you can also see other features developing, and the yellow color is where there's less canopy developing or canopy disappearing over time because the canopy level in May was quite high on that scale, that blue and dark green color. So the canopy level was diminishing quite a bit over the season, and this image now shows you where. So this will allow you then to look at your irrigation system or look at soil conditions and try to figure out why are vines growing less in certain areas. So very, very useful tool just to do visual analysis. The thermal method, again, Landsat 9 will increase the data. This OpenET website will have multiple models running to allow us to understand which models might be most suited to our conditions. And improving these models to fit California crops is a really important area of research right now. And that's one of our biggest limitations. I think maybe Joel and Daniele may be talking on this more. But here's just an example of some of the challenges of applying the thermal method here. This is some work done in a cornfield in eastern Nebraska. And what they're showing you, the solid black line, that's ET data coming from a flux tower in the field. And those colored symbols are estimates of the evapotranspiration by different models using that thermal data. I've circled one measurement time there, and you can see that the 4 different values there are quite a bit different from each other. So that's one of the challenges. These models are right now may not provide good data for a certain condition until we can refine them for the crops that we're working on. The other issue is that you have gaps in the data where there was no satellite readings due to cloud cover, one of our challenges. So my suggestion at this point with you as a farmer using this data, once we can have access to it from the OpenET website and others, just observe the data and see how you can, how it relates to what you're doing. And I think over time, though, this will be a very important tool for us to use. So with that, thank you very much. I appreciate your attention.
Thank you, Mark. I think we do have some questions for you, which we will get to during the Q&A session. So thanks for creating interest in questions, and you gave us a lot of good ideas there. So next up, we've got Dr. Joel Kimmelshoe, and he's going to talk about remote sensing-based estimation of consumptive water use at water district and groundwater basin levels. And Joel is the owner and principal soil and ag scientist for LandIQ. Thank you, Joel.
Thanks a lot. I appreciate it. Can you hear me okay?
We can hear you and we can see your presentation.
Okay, great. Thanks. I couldn't have asked for a better introduction from Mark with regards to the kind of the background of remote sensing and the pieces. So I'm going to jump right into it. That was well played. Somebody was thinking when they put the series together on the slides. Just one slide on LandIQ. We're a private research consulting firm, and basically the way I like to talk about what we do is we take a lot of what is produced in academic environments, of which I came from myself, and apply it to large landscapes on the ground for growers. And in our case, we mostly work with GSAs, groundwater sustainability agencies, irrigation districts, entities like that for application of the research. Our firm is made up of 2 technical disciplines. That's land-based scientists and spatial scientists. So we kind of marry the 2 together and learn from each other and work with each other. I always say I'm a soil scientist agronomist. I grew up on a farm in Butte County. Our family still farms there today, but I'm not going to fake it as a remote sensing scientist, and the reverse is true for our spatial scientists. So it's a nice marriage of what we do. I'm going to start off talking about, well, the presentation is going to focus on kind of 2 main areas. One is land use mapping, spatial land use mapping, and then also I'm going to talk about consumptive use or evapotranspiration mapping that we do for a number of entities in the South Valley.
So we can hear you clearly, but your audio is kind of going louder and then softer. So if you can just either move closer to your microphone or plug the microphone in a little bit more, that might help.
Sure, I'll do this. Here, let me do this real quick. Is that better? Can you hear me okay now?
Yeah, we'll have to just see if it's waving, but we can hear you no matter what. So just keep going. You're doing great.
All right, I'll be I'll talk as clearly as I can. So we're the contractor that does the statewide crop mapping for the California Department of Water Resources. And that contract where we map every single agricultural field in the state of California from Mexico to Oregon, Nevada to the Pacific Ocean, including grapes, of course. And that information is used mostly for, well, was required by the Sustainable Groundwater Management Act, and is used in a variety of other purposes. And I'm going to introduce this from the standpoint of how we use it in our ET work as well. But first, I'm going to talk about our land use mapping. Right now in California, there's about 9.55 million acres of agriculture fields. And before we also map the outer boundary of urban areas. And just for your next dinner time conversation, I thought when we started mapping urban areas, it would be about 20% of agricultural areas. But actually it's about half as much, which was amazing to me. It's a big footprint too. So just kind of gets back to the conversations we all have every day about water use in California and who's using it and things like that. These are slides that we prepare for the California Department of Water Resources, and the DWR is split up into 4 regions: North, North Central, South Central, and South. But gives you an idea of the crop, kind of zoomed in on the state and our crop mapping, gives you an idea of the distribution of crops in California, as well as what crops are grown in which region. And this is a northern region, lots of rice, walnuts, almonds, etc. This is the North Central region, which contains a large diversity of crops, including grapes, almonds, walnuts, corn, etc. And a lot of the areas that we're talking about today. It's about 1.7 million acres of agriculture. And then the South Central region is the large one of them all, of the 4 in the state, and that's about nearly 5 million acres, which includes all of the rest of the San Joaquin Valley, as well as the Salinas Valley and areas down into Kern County. We've produced, so for those of you who like to use this crop mapping information, it's publicly available for free through DWR. You can just Google DWR Land Use Viewer, Land Use Download. You can download the whole state or county or whatever you prefer. That is available for the years 2014, 2016, and for beginning in 2018, we now have implemented multi-cropping. So I call it all crops everywhere all the time. 2014 and 2016 are main season crops only. And this is a shot of the 4th region within DWR, the southern region, which is a very different crop system in many cases than the rest of the state. So how do we do this work? We delineate the irrigated footprint of every field in California. Yes, that's true, we did, and it's the irrigated area only. It's not parcel size, not parcel boundaries, it's actually irrigated footprint. So it cuts out farm shops and homes and things and roads that are greater than 10 feet. So if you're in need of, and in the regulatory environment that we're in right now in California, it's very common to be in need of a true irrigated footprint. Minimum field size is 2 acres. Many times it's less. For example, we do this type of mapping for the California Avocado Commission, the Almond Board of California, Walnut Board of California, a lot of different commodity groups. And particularly the Avocado Commission asks us to do it down to about 1/2 acre because many of their groves are that small. The overall accuracy is about 97.6%, and we map about 50 different crops. How do we calculate the overall accuracy? That's through efforts that we conduct related to what we call ground truthing. And that's the best way and really the most independent way to calculate your accuracy. So during the year at different areas of the state at different times, depending upon when crops are growing and rotational schemes, we'll drive and collect on iPads with our collector what's going on the side of the road. And we drive about 15,000 miles a year in different areas. It's a big effort, but the purpose in having that information is to ensure that we have what we call a calibration data set for calibrating our remotely sensed models to predict what the crop is, and then also a validation data set, which also is important to calculate accuracies. So in the end, basically, we use a larger portion of that data set from ground truthing to calibrate the model, say this is what an almond orchard looks like, or this is what a vineyard looks like 3,000 times, create a fingerprint for that vineyard, and then dust the rest of the crime scene where we didn't drive by, and what's the probability of predicting that that fingerprint matches within that field boundary that I talked about before. The part of that ground truthing data set that we do not put into the model, we hold back, pretend we never drove by it, don't know what it was, put it in the model, try to predict it, We do predict it, and then we compare what we predicted with what we actually saw, because we saw, yes, but we did drive by it. And so we know what was there, and we logged it, and that's where the accuracies come into play. Grapes, actually, some crops were higher in accuracies than others. Permanent crops notoriously are higher because we can do them year over year over year. Grapes, believe it or not, were actually about 99% accurate. So this is some images that I clipped out of our crop mapping of just wine grapes in the Lodi area in the upper left-hand corner. Again, minimum field size is about 2 acres. Many times it's less. Our overall accuracy of grapes is about 99%. And the irrigated footprint of the vineyard only is used. And you can see that on the bottom right-hand image that is on this slide. And we cut out farm shops and homes and things like that, or fallow fields like in the center of this image on the right-hand side. The uses for this mapping are many, and comes down to water management. A lot of our clients, irrigation districts and GSAs and coalition, water quality coalition, use it for water management, regulatory compliance, production planning, maybe some studies they'd like to do with regards to the proximity to other crops in other areas. But having a base map of crop mapping in whatever area you're thinking about is very valuable with regards to implementing and using that data to create answer questions. And these are the accuracy matrices that we put together depending upon, this was one that was done for a study we did in Butte County, depending upon what areas you're looking at and what crops you're looking at. So that's an introduction to that crop mapping. And I want to just say that that's a really important part in the ET work that we do. So we work for a number of GSAs and irrigation districts in the South Valley. They're listed here. About 30 to 35 different crops, multiple water sources, supports a variety of different allocation methods, meaning how much groundwater can you pump, what are you allocated to use, things like that. So the ET component, how much water are your crops evapotranspiring, is very important in an overall water budget. It's the biggest outflow of a water budget. And so that's the piece that we measure, not applied water, but consumed, the ET. We do that through ground truthing. Shocking, I know. And the ground truthing here isn't driving by fields like we do in with land use, but we put in actually what are called surface renewal or eddy covariance stations. I won't go into those details, but their purpose is to measure the parameters necessary to calculate actual ET on the ground. We do that in about 100 different places in the South Valley with different types of stations. And we use that information to calibrate the models and validate the results. It also, and Mark mentioned when cloud cover occurs, that's a challenge with remotely sensed ET, and it is. So when cloud cover occurs in our areas, we actually have the stations to fall back on for actual on-the-ground measurements that help us extrapolate that across the landscape when cloud cover was on the image. This is a map on the right-hand side of the green dots are stations that we put up in various places, and it's, you know, the reason why we're starting in the South Valley is that's the most critically overdrafted groundwater basin in the state, and it's working north, and it's driven by Sigma, and the purpose is to provide that information for the groundwater sustainability plans and water management moving forward. Again, we incorporate crop type into this analysis. This is a North Kern Water Storage District. There's some images that I'm going to roll through really quickly, and the black dots on this image in the middle are the stations that exist within North Kern. We distribute those according to crop type, percentage of crop type, and then you can see on the lower right-hand corner, we have a number of different stations throughout the South Valley. Again, it's harder to do this type of work. It takes more time to do this type of work, but the purpose, because water resources are so stretched, is to get as much ground truthing, actual ET information as possible to make the best estimates of consumed water, the tightest, least variable estimates of consumed water for better water management.
5 minutes.
Thank you. We do a lot of measurements in grapes in the South Valley, both in wine grapes and in table grapes. And these are the measurements, the parameters that are measured by the stations. I talked about already about incorporation of crop type, and we bin by crop type, so we analyze by crop type. Most remotely sensed ET estimates analyze across a landscape, from the least consuming area to the most consuming area. We bin that by crop type in an effort to, again, reduce variability as much as possible. These are month-by-month results that we deliver within 25 days from the end of the prior month to our clients. They find it very useful from the standpoint of managing their water. And in fact, we have a couple irrigation districts, GSAs now, that are actually charging their growers not by the acres that they irrigate for water, not by the acre feet that are applied, but rather by the water in acre feet or inches of water that is consumed by the crop. Again, because that's the largest outflow of the water balance. We deliver three things. We deliver field by field crop type, like I talked before. So those irrigation districts and GSAs can use that in their reporting or planning or whatever requirements that they might want. It's consistent with the results for DWR. The DWR results are running about 2 years later, and shockingly enough, people want stuff faster nowadays. We also deliver field by field precipitation. On our stations, we have a number of rain gauges, and it allows us to incorporate in those point data to create spatial maps of precipitation. So now, as the image implies on the right-hand side, we can apply a certain precipitation to a certain field. You'd be surprised about how much the growers and the districts in the South Valley care about every quarter inch of precipitation. It's really become more important than I really anticipated. And then also the ET that I showed before. Just some figures from grapes. This is the last 12 months on the top figure. And some other crops on the bottom figure for 2020. We also work with Thule Tech. I want to make a shout out to them. From certain crops, we use their technology. It's a cost-effective way for us to replicate across fields and incorporate even more stations. We're kind of data-hungry, data scavengers. We ground truth like crazy, and that's important from the standpoint, again, of calibration and validation of our models. We provide accuracy assessments on a monthly basis with regard, and it's related to the reporting. And we look at things from an agronomic standpoint. Remember when I started off, and I'm almost complete here, start off that we are both land-based scientists, soil scientists, agronomists, and spatial scientists together. One of the validation tools that we use is, quite frankly, our knowledge of agronomics and on-the-ground conditions and how things should look when you're talking about a certain crop. And I won't go into the details of this figure, but you better have, in most months, better have consumed water less than applied or total received water. And this is a comparison, this figure of applied and rainfall, the total amount of water that's received by about 30 almond orchards in the South Valley as compared to consumed water. In September, the reverse is true, and that's obviously an effect of stopping irrigation, starting harvest, pulse split and harvest. So I want to thank the Lodi Winegrape Growers and Commission for allowing me to speak today. I hope it was helpful for some of you, and if you have any questions, I guess we'll address those at the end. So thanks.
Thank you so much, Joel. I have a ton of questions for you, so we'll see if the attendees have their questions matter more than mine. We're going to take a little break right now. So 10:10, we're taking a break, and we will be back, and we're going to start right at 10:20 because our next presenters have a lot of information to give you as well, and we want to make sure we give them all of their minutes that they need. So everyone, you have a 10-minute break, and we will be back at 10:20 a.m. on the dot. So see if you can sign in just a little early. We'll see you then. And Marnus, if you would like to try and share your slides, you're more than welcome to do that with me during this break. I can make you the presenter.
Stephanie, just a question. How do I upload a handout? in this presentation?
Yeah, so just send it over to me via email, and as long as it's a PDF, I can upload it, or I can convert it during the break and upload it for you.
Okay, because what was interesting is in the presentation, they referenced the particle size analysis with Maya's presentation, and we actually have a very comprehensive report system on that, as well as on the water and on our ITEST water report format will make it make the interpretation of these results for the growers very easy to interpret.
Oh, anything that makes our lives easier, yes, please. If you are able to email it over right now, then I can add it in. Yeah, that's great.
I'm going to send it over to you in a minute.
Okay, and then during the Q&A session, or if there's time in your presentation, you could just make a call out to it to make sure they know it's there. Yeah.
Okay, thank you.
Thank you. Thanks for thinking of that. Yeah, so Marnus, I'm going to make you the presenter right now, and everyone can hear, just so you know, this is being recorded, everyone can hear us in this little chat time right now. So this isn't private. So I'm going to make you the presenter, and then you'll have a little thing that will allow you to share your screen.
All right, perfect.
And what time is it over there? Is it nighttime?
7 to 10, yeah, 10 past 7 at night.
Well, thank you for the dedication.
Of course. And can you see my screen, the presentation?
I can, yeah.
Okay, all right. I see stop showing screen, so that I'll do once I'm done.
So you can now, if you do, slideshow view show, it'll show it will be less messy. So right now we can see like all of your extra stuff, yeah.
So that's better. And then when I'm done, should I then change presenter back to you, I assume?
You actually don't even have to worry about that. I handle that on the back end. So
so you
don't even have to worry about that.
Control just briefly, pretend that we have some power, and then you take it straight back.
Absolutely. That's how this works. You're figuring it out very quickly. Okay, well, enjoy the rest of your 7 minutes of a break, and we will just, why don't I, Dirk, I'll just pass it over to you, and you can go ahead and have your slides pulled up so that, because you're going first, right?
Actually, not necessary, because Marna is going to present. So I will just do a brief introduction, and then Marna is going to go straight to his opening slide, and then we go in.
Oh, okay, so you don't need to do any slides, Dirk.
Not now, because I'm going to share with you those handouts, and
okay.
I would rather have Marna's talk, because I think that will be very interesting and very relevant.
Okay, perfect. Then we'll just keep you, Marnus, as the presenter, and when we come back on at 10:20, I'll just quickly give the title of your presentation and both of your names, and then you can give your better introduction and go into the meat of the talk.
Perfect.
I think, to be honest, Stephanie, I think you can actually introduce Marnus right away. Let him go, and at the very end of the Q&A, I will just wrap it up. That way, it's just nice and clean. Okay,
so let me just make sure I understand. So you want me to just introduce only Marnus?
You can introduce the both of us, but okay. I'm not going to say anything prior to the presentation. I'd rather just wrap it up at the end.
Sounds great. Perfect. It's a plan. We have a plan. So just a funny side note, when we have these breaks, I'm sitting on my front porch, and we do have some people who kind of wander on the street. So I always get a little nervous when I leave the computer to run inside and run back outside. So you two now know that if the computer starts wandering, we know what happened. I tried to hide it a little bit.
Send us your GPS location, we'll send help.
That's great.
We'll write down any number plates we see as fast as we can.
Thank you. Okay, I'll see you in 5 minutes. Thanks.
Thank you, Marnus. as jy my kan hoor, dit was die tegniese noot was in die chatbox gewees. Ek weet nie of jy die chatbox gesien het nie.
Sê net hulle rekord die ding.
Ja, my so reg het gesê, is welkom. You can check your presentation. Is myne al wat ek na dit vir jou gestuur het. Ek wou net weet of jy daai chat kon gesien het.
Ongesien.
Hierdie GoToWebinar is vrek goed georganiseer. Hier is oor die 90 produsente op hierdie call, net dat jy weet. Hoe gaan dit met Mackenzie?
Nee, heel okay. Sy kap aan.
Presies dit. Alright, ek gaan afgaan en volg ek jou op die webinar.
All right, everyone, I hope you had a nice 10-minute break there. We are going to get started to talk about soil zoning for implementation of optimized and variable rate irrigation. We've got presenters coming to you from Agritechnovation. Dirk Bernard is the president and Marnus Ferreira is the head soil scientist, and he's traveling virtually quite a ways for us to present. We'll pass it over to you, Marnus. Thanks for being here, both of you.
Thank you very much, Stephanie. All right, it's thanks to the Winegrape Commission. Really appreciate that we could be here today and chat to you guys about something that, well, I'm extremely passionate about, and our company is as well, and that's about soil. So every now and again they let me out of a soil pit to come speak to the rest of civilization, and today is such a day. Right, sorry I'm a bit late. I just came from another water management summit here in Cape Town, South Africa. And Joel, I liked what you said. I just caught the back end of your presentation about boots in the ground. That's our philosophy as well. So just a very brief introduction about our company and where we hail from. So this is our entire global footprint where we do business on a daily basis. We're just starting out in South America, lots of exciting opportunities there, but obviously the North American market is an important one for us. And it's always nice when you get to transfer knowledge from all the sites that we work in and crisscross information and new plans and new ideas to growers globally. And that I think that makes us quite strong. Here's we've got a platform. I believe some guys were talking about layering information, and that's really what this is about, but I'm not going to go into too much detail. We can share some data afterwards, but we have a platform. We have approximately 6,300 farms on there, which equates to about 2.3 million hectares. And in today's presentation, one of the international Commission for Irrigation and Drainage gave the keynote address, and he spoke about the 300 million hectares of irrigable land globally. So we still have quite a while to go to get everyone on the system, but we're slowly getting there. All right, soil. So there's a lot I can say about soil, and I'm like I said, I'm very passionate. So if you let me go, I'm going to run with this forever. So I've cut my slides down to stop me. But yeah, the main message I want to talk about today, and sort of a brief version of what I spoke about earlier today, was the fact that we have a lot of variation on farm level. So I speak about management at field level, because that's really what it's about. We have a lot of technology to assist growers. We have a lot of knowledge to assist growers, but I'm going to talk about one of the basic foundations which we need to get right, understand, and it makes everything else, especially irrigation, much, much easier. So I'm going to be talking about the soil physical properties. I'm going to touch on water quality, and then obviously I'm going to touch on climate as well. All right, so the first thing I'm going to talk about briefly is texture. So on the right, I've loaded up a scanning electron microscope image of a sand particle. The big ones are sand. I don't know if you can see my mouse. Those are sand particles, and the little particles are kaolinitic clay. So those are clay squished sandwiched into those sand grains, and that's what it looks like. And that's sort of what a soil scientist, to a certain extent, has in his or her head when they start assessing a profile pit, is if you're looking at bulk densities and compaction, things like that. This is what we think about. And if you visualize how water moves through soil, this is one of the key components to talk about, is the clay particles. And on the left here, I've got some numbers. So I've got the mineral, I've got the cation exchange capacity, and I've got the specific surface area. Because we're talking about irrigation and you're talking about soil, the main thing is, one of the big drivers, of course, is the specific surface area. Because if you're putting water down into a soil, your drainage speed, your percolation rate, all that stuff is determined largely by your surface area, assuming soil is not compacted. And the reason for that is quite simple. I know we have some soil scientists on the call, so bear with me, but for everyone else, this is quite interesting stuff. So quartz, which is just our sand grains, the mineral responsible for the majority of our sand, it's got a surface area of 15 to 150 feet squared per ounce. So every ounce of sand that you pick up has got a surface area of about 15 to 150 square feet. So if you take that sand grain and you were to tear it apart and lay it flat on surface, that would be your total surface area. So not very big. If you're looking at kaolinitic clay, that moves up to 150 to about 1,500 square feet per ounce. And if you go to a smectite clay, which I'm going to show in the next slide, up to 250,000 square foot per ounce. So that is a massive surface area. If you were to take each clay particle, break it apart and lay it flat, that would be the surface area per ounce of soil. So water needs to move through all these gaps, and it takes a very long time. And that's generally why our water drainage through clay is so very slow, is because it has to move through all these gaps. So even though clay is highly porous, it moves very, very slowly. All right, so the picture on the left, again, SEM 10 microns, is of kaolinitic clay. So you can see it's all neatly bound, looks like little books. And that's why the charge isn't as big. We don't have as many breakage surfaces to cause charge, much more organized structure, much less surface area. On the right, we have a slightly weathered smectite clay, and you can see all those little sort of fields open up. It's highly porous. It's a very, very porous sponge. So there's lots of gaps to move through. So water takes a very long time to flow through all of that. And it's obviously highly interactive, highly charged. And that's the reason why clay and water interact the way they do. All right, so taking that into account, if we're looking at a soil from a physical aspect, which we try and do, which we should do, if these are two photos of profile pits, we have certain issues with some soil. So I know Lodi is blessed with very good soils, generally speaking. You know, guys have some very nice dirt, but there are still some stuff that we find. There are still variation in the field that we need to know about before we build an irrigation system, before we do a design. It's much better to understand what's actually going on beneath surface, because that's where we're putting our water. And that's what these two slides show. So on both of them, we have some free lime buildup. On the right, you can see even at 2 feet, we do start increasing free lime, and then at 3 feet, it starts to become quite dense. And down to 4 feet, we're starting to get, you know, some petrocalcic layers. It really starts to harden up. And even from 3 feet down, we will start to see quite a dramatic decrease in water penetration. So you need to consider that. You're effectively irrigating 2 feet of soil if you're not berming up. So it's a vast difference to having a soil that you're irrigating down to 4 feet, or you know, potentially thinking about doing that. And an area on the right is going to behave very different to your normal salty loams or loams that you find in Lodi, your deeper, well-drained stuff. So if you start seeing this variation in the field because of your water issues, it's because of this kind of variation. All right, so you can see it over there. Same thing on this slide. So at about 1.5 feet, we see a drastic contrast because of those alluvial sedimentations. On the top, we have salty loams, and below that, we have the stratified coarse sand intermixed with mica and pebbles. And that really stops water penetration. I mean, water will eventually go into it, but as you guys know, from a very fine soil, you really struggle to get water out of the fine particles and into a coarser medium, such as the fine stratified sand. So it really starts stopping water. You get water pushing back up into the system, and obviously you're not going to get deep root penetration. You're not going to get withdrawal from a deep source. And again, it influences your irrigation. So if you know about this beforehand, you can design the system to put soil like this into one irrigation block, or change your irrigation method for that area that's affected by this physical characteristic. And then your deep soils, or your even shallower soils, or whatever it might be, you put in a different system. From the design get-go, from an engineering point, it's very, very useful to know the stuff in advance. Then management of water becomes much easier. Obviously still a lot of challenges, but it really, really makes it a lot easier in the end. So another example here, much less visible straight off the bat, but again, we've got quite sandy soil in this case, and then we have this coarse layer deposited alluvially, and then below that we continue with the same soil. So all this needed was a deep mixing action. Some soils, like the carbonates, shouldn't be mixed, but in this case, all the soil needed was a very nice deep mixing action, and we wouldn't have had the crop failure to such a large extent that we did have here, just because we're struggling with water penetration. And they were treating the whole vineyard homogeneously, which obviously was a mistake. All right, and just some other examples of the kind of variation that we see in soil. On the left, vine, heavily compacted soils, not a deep ripping action that they should have taken. Lots of good examples of soil cultivation there in the Central Valley and in the Lodi area, Northern California. There's lots of options to prepare the soil correctly, but again, you need to know what the problem is, what to address, because soil variation is massive. One in the middle, we've got some citrus, and where the hammer is, that entire area where we don't get a root zone is because of subsoil wetness. We have a bit of broken dairy pan that's cemented still in places, but again, soil preparation wasn't done correctly. Fortunately, they did berm up, which I think saved the day at the end. And then on the right, we've got some very, very highly oxidized, deep, well-drained soils. All right, and then obviously we've got water quality to contend with as well. I'm not going to go into this, don't have enough time, but these are the kind of variations, again, that we have to deal with. And if you're sitting with all these tons of variation, it makes your life a lot more difficult. So just to express this in terms of an equation to make it for some people a bit easier. Other people hate equations. I apologize for that, but here we go. And all I want to show you is that we've got a water system in soil, obviously. So we've got DS, our change in soil storage, precipitation, deep seepage, runoff, ET, all that. But what I want to make the point here is if you have that system for one orchard, you know, one block, that's great. But the problem is within that block, we normally see variations of this equation. So what I mean by that is an area might require artificial drainage, or you might not have deep seepage, or you have water that's running through the profile and gets stuck and builds back up again. So the moment you have variation in your block in terms of your soil water interaction, it makes again your life difficult. How do you, after the fact, after the design, make changes for that? It is possible. You can put in, you can make changes to your irrigation system. You can put in taps. You can make alterations, but always much easier from the get-go to know exactly what it is, what the best results are going to be based on something as simple as classifying your soil and understanding exactly what's underneath. So here we've got under nets, we've got again a block where we needed artificial drainage because our deep seepage was, you know, there was a problem with that. We weren't getting deep penetration, water was building up. So now you put in artificial drainage, and from an irrigation point of view, if you're looking at a block system, it helps because now all of a sudden you're getting closer to a homogeneous block, right? You turn the tap on, your dripper or your microjet or your flood irrigation runs, and all of a sudden you have a much more homogeneous water-soil interaction as your water runs through the profile. And it really comes down to something as basic as this. And again, more drivers. We have soil physical properties. We have infiltration issues because of droplet energy or chemical composition in the soil, high sodiums, whatever the case might be, bulk density. All these things add to variation. So here you can see again soil physical properties. On the left, we have a stone layer in the subsoil, which normally can help quite a bit, but it was cemented with Duripan, makes root penetration and water penetration hard. Picture in the middle, very nice, deep, sandy loam soil, beautiful root penetration, great pot. You can see the pot there. Soil preparation was good. And again, the picture on the right, where we have drippers emitting onto a surface that contains just a little bit more silt than the rest of the profile. And underneath that silty sand composition, the dry areas, very coarse sand. And again, once water's inside a sponge, i.e. the salt and sand mixture, it likes to stay in that. So we dug a profile pit, trees were looking poor, and this is what we saw. We saw wetting, but only in the areas where the soil texture was the same. So wherever the emitter penetrated the soil, it stayed in that soil texture. So again, just a good deep mixing would have been better in this situation.
5 minutes.
Thank you. Yeah, I hear there was, you guys did talk about plant available water capacity. So for sake of time, I'm not going to go into that too much, but again, sand, much lower plant available water capacity. I apologize, some of the values on the graph are still in millimeters, but you have between half an inch or sometimes an inch of available water for sand, and then you try and irrigate that together with loam, you're going to end up with stress in the plant. And most of farmers globally tend to over irrigate, and again a plant is much worse off with too much water than too little water. It really goes into stress a long time, and it struggles to get out of that, and we see the long-term effect much more readily on an over irrigated field. And with global tendencies to preserve water and our responsibility globally for that, it's important, better for the crop to rather have a little bit less water than to completely over irrigate. Not condoning not irrigating, but just saying. All right, for sake of time, we have soil issues. Water quality plays an important role, but even if you have poor water quality, if you have access to flood irrigation and you can emit a lot of water at the start of the season to at least flush out those salts, that is good practice. And more variation. We have crop changes. You even have variation, obviously, in terms of if you're working with one crop just inside your cultivar, you have micro variation. So the best way to deal with that, as I've mentioned in the start, just I was hoping I didn't run out of time, was to do a proper investigation of your soils, do a block layout with your engineering team, your irrigation engineering team, have the soil guys, the crop guys, the irrigation guys sit together and design a block that can work for you. Even if it's on a large ranch scale, a smaller scale, small adjustments can make massive differences. So this is I can't remember exactly where this was. Not Paso Robles, I see it's quite flat. But yeah, so an area like this, a very easy solution would have been block in the top right is already split off, but that's just happened to have been done like that. Block on the left, you have very sandy soil in patches, and then you have a salt loam in the south. And trying to irrigate, we saw massive stress, obviously, in the sand. The loamy sand wasn't performing great. Salt loams were doing very well because of their high water holding capacity. And it's just these variations where we want to split blocks from the start, or even afterwards come in and split blocks, just to really help management. And just lastly, an interesting trial we did with Valley, I apologize. You'll see the different areas. What we did is we loaded 3 different types of map on that Valley pivot. And this is kind of technology is becoming more and more available, where you run 40% irrigation versus 60 versus 100 on one go to try and pull all those probes level, and you play with it. We made 3 maps, kept it very simple. We had a 40, 60, 100, and the reason we had a 40 is it's a soil that's very poorly drained, and that soil tends to be over irrigated. So we give it less, and then the third one we gave it a 80% of normal, and just to refill the profile. And we got fantastic root development at the end of the season, even down up to 24, 32 inches. We got withdrawal of water, and that's what you want. It means we got the oxygen to water ratio correct. So thank you, Stephanie, and the rest of the attendees. I apologize, I ran through that quite a bit. I see my presentation, Dirk, apologies, the last slide switched. That's our SA contact number, but Dirk, you'll send through the .com one.
Thank you, Marnus.
Yeah.
Yes, I think our contact details, and we did share some handouts on the platform, so you will get our contact details there, and we would be happy to come and visit you for a consultation to show you what we got and what we have to offer.
Thank you, Marnus and Dirk. That was great information, and you had beautiful slides. I'm glad you let Marnus out of the soil pit so that he could talk to us today. So next up, we have Dr. Tapan Patik. He is the Climate Adaptation Specialist for UC Merced, and he's going to be talking with us today about climate change implications for the San Joaquin Valley grape and wine industry. So thank you, Tapan, and we'll look forward to hearing from you next. You are muted. You're going to have to unmute yourself. Now, yeah, there you go.
All right. Can you hear me okay?
Yep, we can hear you and we can see your slides.
All right. So thanks, Stephanie, for the introduction, and thanks for inviting me to give this talk. My talk is more sort of a general overview of what's happening with the climate change and what sort of implications it can have on the San Joaquin Valley, especially on the grape. So just a very brief outline. I'll start with a few slides about talking about the climate basics, the jargons that we use in the climate science, and talk more specific about what's happening with the temperature, precipitation extremes, snowpack, etc. And then second half of my talk will be more focused on agricultural impacts, and some of them are directly related to the wine grapes and grapes in general. And the last slide, I do want to mention about a project that we are just getting started. We have some information on that, and then followed by the summary and research directions. So I just wanted to distinguish one thing. We talk about climate variability, climate change quite a lot. You see these two slides are the graphs time series, and you hear El Nino, La Niñas, and so that kind of oscillations in the media sometimes. And so the upper time series you see, it's one of many indicators that define that El Nino, La Nina southern oscillations, which is called ENSO. And if you see the oscillations, they are more narrowly driven. So, you know, they're orange and blue, which is the warmer than normal oceanic temperatures, versus the blue is the cooler than normal temperatures. And so their oscillations are very narrow, maybe from 6 months to about 2 years or so. The bottom one is also oceanic temperature oscillations in the Pacific, and their oscillations is more larger scale on a decadal oscillations, more sort of, so even it's a decade or even a multi-decade. So when we think about variability, these are the natural variabilities that do influence climate quite a lot across the globe, and then there is some influence in California as well. So when we think about variability, it's a measure of shorter term fluctuations around that long-term average. And the long-term average is, you know, you define it by maybe a 30 years window or shorter term averages, and you see the fluctuations. So it's more shorter term. When we think about climate change, as opposed to the variability, it's more of a gradual change. So depending on which variable we are focusing on, that change could be either increasing or decreasing. So when we think about temperatures, you typically see an increasing statistically significant trend, and that's over a longer period of time, so maybe 50 years or even 100 years. And as opposed to that, when we think about the snowpack, there is a declining trend. Chill hours, there's a declining trend. So depending on the variable of focus, this could be different. So just in a summary, variability is a shorter term fluctuation. Climate change is more longer term continuous change, and that needs to be statistically significant. And so that is what this talk is mostly focused on, to see what sort of changes, gradual changes we have seen or we are expected to see in California, and what sort of impacts it can have in agriculture. So NOAA, National Oceanic and Atmospheric Administration, they update their climate normals, and the climate normals is a typical 30 years average weather, and that do define climate for different regions. And so they update this normals every 10 years. And so the last normal was from 1991 till 2020. Oh, sorry, the old normal was 1981 till 2010, and the new normal is 1991 to 2020. So that's a moving 10 years window. And the recent new normal just came last week. And as you can see, all the orange that you see, and even if you focus on just California, the entire state is in that orange and reddish color, which means that even from last normal to this normal, so in that 10 years window, the temperature, mean average temperature, have increased at the rate anywhere from 0.5 to 1 degrees Fahrenheit. So it's just the 10 years change. There are some regions in the United States that did see somewhat cooler or the cooler conditions in the recent 10 years, but on an average for the whole United States, it's a warming conditions in even in 10 years window. So if we focus on California, and if we look at last 120 years or so, this slide, I pulled it from Western Region Climate Center. And so if you see E and F, which is the Sacramento Delta region and San Joaquin Valley, and the blue bar shows the minimum temperature increases, and the red bar shows the maximum temperature increases. So as you can see, the rate at which the minimum temperature have increased in last 100+ years is significantly higher than the maximum temperature and the average temperatures. So there is a lot of negative implications on because of that. And then some of them I'll talk about it in the next few slides. But as you can see, the valley has one of the largest increase in the minimum temperatures, and along with the coastal region of California. This is another way of showing the same information or similar information. If you look at this vertical line, which is a baseline temperature from 1949 to 2005, and orange shows the deviation from that baseline temperature in the maximum temperature window, and the green line shows the deviation from that baseline temperature in the minimum temperatures. So again, if you see Sacramento Delta region, the deviation from the baseline in the maximum is maybe from 1 or 2 degrees, whereas the minimum temperatures have deviated anywhere from 2 to 4 degrees in the valley. And the same with even the the San Joaquin Valley is also in the 2 to 4 degrees Fahrenheit increase temperature deviation window. Okay, so here is a temperature trend just for the Lodi region. I pulled this slide from, I got this graph from CalAdapt, which is an online tool. It's a multi-agency collaboration developed for California. And as you can see, even if you focus on the observed historical temperatures for Lodi, the average is about 73, 74 degrees Fahrenheit. That's like 1960 to 1990. You can change the slide and see, you can decide your yearly time frame to see what sort of average temperatures are for that time frame. But if you compare it with the future projections, roughly by end of the century, so 2070 to 2099, the average temperature would be about 83. So it's almost 10 degrees Fahrenheit increase is projected for this region. So here is a precipitation trend, and I have 2 time series, one for Sacramento, the Northern California, and Ventura, which is a Southern California, just to compare. As you can see, that includes the observation from the past as well as the projections with respect to high emission scenarios. And you see a lot of chaos and a lot of different colors in this time series that represent different climate models that give that projections. So as you can see, there is a lot of uncertainty. But one thing to point out here is there is almost no trend, either drying or wetting conditions in the future. So it's not clear whether there is a distinctive trend when you talk about precipitation into the future. What it shows is that we are going to see a lot of variability, and so California is as we have seen in the past, is going to be vulnerable to both flood type conditions as well as drought conditions. Another confidence climate modeling community has when it comes to precipitation is that even if we don't have a clear understanding of the precipitation trend, there is a clear confidence on overall wet season for the state. So the entire wet season for the state is shrinking, and it's going to shrink even further under future climate. So even if we get the same amount of precipitation, it could come in more single-day extreme precipitation type events in the future, or the drought conditions. So extreme heat is another big major factor when it comes to agricultural impacts. And if we again focus on Lodi, and if you look at the extreme heat, which is defined as 98th percentile temperature for the time frame that was for which we want to see that 98th percentile. So in this case, again, it's 1960 to 1990, which is a default, and that 98th percentile temperature threshold is roughly about 101 degrees Fahrenheit for Lodi region. So what this graph shows here is that under observed conditions, you would expect, or it's observed on an average 4 days when temperature exceeding 101 degrees for this region. When you compare it with the future climate, you would expect 53 days when temperature exceeding that 101 degrees for Lodi region. So, there is a clearly upward trend in number of extreme heat days with the temperature exceeding that threshold. And not just the number of days, but this particular slide shows the distribution of those heat days. So if you see more observed historical years, most of the extreme heat days are concentrated around the summer time frame, so June through September. As you move into the future, those summer days are more denser, so which means that you are going to see more and more extreme heat conditions during summer as compared to the observed data set. But another important thing is that your extreme heat conditions would start as early as May and could last as long as October. And so there is a lot of negative implications from the productivity side, but also when you are managing ag workers, the human health impacts and other aspects of it are also critically important when you think about the agricultural impacts. And again, one of the major heat mitigation strategy is applying more irrigation, and so that could increase the rate of irrigation applications as well to mitigate these heat events. So that's another thing to consider.
5 minutes.
Oh, okay. So I'll just quickly grab through it. So snowpack is our natural water storage, and what the climate models are showing is that we are going to see less and less snowpack under future climate, and that could constrain more on the ag water supply in the future. So let's move on to talk about impacts on agriculture. There is not a lot of simulation models to talk about impacts on yield, but even for some of these row crops or the field crops, you see some negative impacts anywhere from 10% to 30 to 40% depending on the crop. But again, this is just a modeling study, and there is no management or water factor taken into account. So I would still look at as a trend and not the real percentage as a yield decline. But because of the temperature, there is a potential for yield decline. So chill is, as a lot of specialty crops do require number of chill for during the winter time to break the dormancy and go to the uniform flowering and bud break. And under future climate, we'll see or expect to see less and less chill accumulations, anywhere from 30 to 40% decline. We are just doing one interesting study looking at this El Nino, La Nina type oscillations and see how it can impact chill accumulations. And this is one example that, you know, in a Pacific decadal oscillation, when it's in a positive phase, the entire valley can expect to get more chill as opposed to the PDO being negative. And then we are investigating more and more large-scale teleconnection industries to find that connections. Length of the growing season is the time from last spring freeze to first fall freeze. So that the entire time frame is expanding by almost 2 to 3 weeks. So there's a longer growing season, but not to confuse it with the time from emergence to maturity for some of this annual crop. So we did one study on processing tomatoes in the valley, and what we found out is that time from emergence to maturity for processing tomatoes could reduce almost by 21 days, which is almost 3 weeks. And we did not study on the yield impact, but from the physiology perspective, if the time from emergence to maturity is shrinking, that could impact on the fruit size. And so in this case, it could potentially impact tomatoes in this case, and this could be potential for other crops. One positive news about climate change is that in the future, we could see reduced frost risk. We recently published a study for the entire California. What this two graphs shows that in the early century, frost exposure could be reduced by 20 to 50%, or by mid-century, frost exposure or the frost risk could reduce by almost 75% for the whole state. Big implication is also on the pest and disease and weed pressure. We recently published a work on navel orange worm, which is more damaging pest for nut crops in California. And then what we found out that historically there were few counties where you would expect 5th generation of navel orange worm. By end of the century, the entire valley could be a potential to see 5th generation of navel orange worm. And so this is just one pest. This could be potentially expanded to other pests because of that. And this is probably one of my last slides. So we are working on converting weather and climate information into some meaningful decision support system for agricultural community. And so it's a work under construction, but our hope is to create advisory system that includes heat advisory, frost advisory, pest and disease advisory, growing degree days tracking, etc., and keep it open source and freely available to all. This is a USDA funded project, and we recently got additional funding from UC Office of President to continue this work. Just a summary that we are going to see a lot of changes that we are already seeing, and we are going to see in the future climate as well. And there is a clear impact on agriculture. There's a lot of research needs, but I think all those research needs should also take into consideration clientele inputs, and creating solutions based on what their needs and perception is critically important. I'll stop there, and this is my information, so feel free to contact me if you have questions.
Thank you so much, Tapan. That was great information, and I think that gave us a lot to think about, but you packaged it up well for us. So next up, we've got Dr. Khan Kurtaral, who's going to talk to us about practices for preventing and mitigating heat damage in the vineyard. And as many of you know, Khan's the viticultural specialist for UC Davis, based over there at the Oakdale station. So Khan, you are up next, and we'll make sure that we can hear you. There you go.
Okay, there's my screen and my face, I think. All right, let me make this large. Okay, so Daniele asked me to talk about mitigating heat waves and exposure damage to grapevines and how this can be mitigated either with irrigation and some sort of other methods. All right, let me advance this. So as Tapan said, things are slowly getting warmer. Some regions faster than the other. Looking at where I work now, where I do the fundamental research work in Napa, it has moved from a warm region 1 to a somewhat middle of region 2, based on the Winkler index. And then when we look at the daily meantime temperature during the growing season, it's almost a one-to-one related to growing degree day accumulation in these regions. And this is not surprising. We're seeing this across California, except for some counties in the San Joaquin Valley, where it has always been warm, which is usually south of Merced County. There's a shift in the climate in coastal California. Of course, District 11 is not necessarily on the coast, but it certainly has a coastal influence. But as Tapana alluded to it, there is little to no cloud cover now. We have intermittent heat spikes, and there's a general warming trend. The inset here is the precipitation supply from 1920 to about year 2019 in the Lodi area. So the amount of rain we're getting has not changed. It has remained somewhat steady. But of course, there are ups and downs, as you all well know. So consequences of high temperatures of grapevines, of course, immediate responses are exacerbation of water deficits, because there's an increase in vapor pressure deficit. So as vapor pressure deficit increases, there's an increase in evapotranspiration. And therefore, water requirements under a heat stress can be increased. So immediately we start seeing responses that affects the pocketbook. We get initially a smaller berry size, then we get shriveling, then we get a bunch stem necrosis, and then in extreme cases, you might get a crop failure as a consequence of high temperatures. We did a lot of work previously when I was hired at UC, coming from Fresno. They're like, hey, Napa growers, I want to fund this study. Let's look at these colored shade nets. I'm like, why am I doing this work? Because, it was kind of like bizarre at first. So we hung these, shade nets along the canopy, trying to, capture the heat, so on and so forth, or block the heat or reflect the heat. In the end, we end up testing 1, 2, 3, 4 different shade nets. And when we looked at it, of course, the black shade nets was the most, useful one. Because, if you think about it, umbrellas are black because, they're just absorbing the, damaging temperature that might be coming in. And it was the same principle in grapevines as you put nets on them. But of course, there were a lot of questions that was posed to us. They're like, well, can we irrigate these vines more? Like, can you irrigate them right before a heat wave, so on and so forth? What is the molecular marker that's happening with these? So we took the work a little bit further as, we understood the damage of heat waves as we were moving forward. There's a molecular marker for heat and overexposure in grapevines. A lot of the compounds that we deal with in our wine grapes are upregulated by ultraviolet light B. It's a very narrow section in the solar light spectrum. The grapevine can sense this on the leaf and also in the berry. And based on the ripening stimulus and water deficits, which is induced by soluble sugar accumulation in the berry, certain genes are turned on and you have color. But some of these are constitutively defined fluxes. As the grapevine grows, these will be turned on. Some of these will be turned on by ultraviolet light B, which is the purple lines here. And some of the genes will be promoted by ripening and water stress, which gives us, a lot of different compounds in the grape berry. What happens under heat and overexposure stress, one compound in the grape berry gets upregulated, and it's a monoglucoside flavonoid called camphorol. As you increase light and temperature, this thing does not degrade. It just keeps growing. Now, I know a lot of you send your samples to, outfits. They will measure quercetin. Of course, quercetin is, a portion of these compounds. However, it's not a good indicator of these things. Camphorol is the compound that you want to look for in these analyses, but we'll talk about this a little bit later. So we want to look at the vulnerability of Cabernet to solar radiation exposure and heat, and whether increased water availability could palliate these high temperatures. So in order to do this, we looked at gas exchange, stem water potential, berry temperature, moss composition, and skin anthocyanin and flavonols, and how these move about during the season. The work was done at the Oakville station. This was a traditional Napa vineyard, clone of Cabernet on a 110R rootstock. We excluded our solar radiation with a black shade net with a 60% shading factor or not. This was applied 26 days after flowering. And we irrigated 40% of our ET, or we doubled it to 80% of our ET. And it was a factorial arrangement of our treatment. So we had a black shade net with 2 of these irrigations, or controls that did not have any shade nets with 2 of these irrigations as well. So a total of 4 treatments. Of course, when you look at these regions, you read about them in the back of the wine bottles. You move to these regions from Fresno, thinking like, you're going to get away from the heat. That is not so. When I look at these regions, you have to look at the whole season over the course of many, many years. So this graph is, summarizing a 10-year period of daily max temperatures and daily or mean daily temperatures as well. As you can see, there are many heat spikes that are happening in these regions that are, supposedly, cool regions compared to where, grapes are mainly grown. But I want to point out that, temperatures in excess of 40 degrees Celsius, above 105 degrees, are not uncommon in these regions, and they can last for many, many days. For example, the example I'm showing you here in this talk, we had a heat spike 102 days after flowering. Temperatures reached 117 degrees Fahrenheit, and they stayed there for 4 days, right before harvest. Of course, as you put nets, you're going to exclude solar radiation. The solar radiation spectra here, I'm showing you from 300 nanometers to 1,000 nanometers. The exposed that did not have the shade cloth on it is of course having a lot of irradiance on it. Nothing's impeded. But if I put the partial solar radiation exclusion on it with the net, I will remove roughly about 60% of the solar radiation to the grapevine canopy where these things were hanging. And of course, this is going to have some effects. Here we're looking at the stem water potential throughout the season based on when we started irrigating. Of course, if I double the amount of water, I'm going to have a much better plant water status. But as you can see, there's not a whole lot of difference whether I shade the grapevines or I do not shade the grapevines. The main effect here is the effect of irrigation on the stem water potential. Shading did not affect it that much. When I look at the seasonal averages of net carbon assimilation, evapotranspiration, or the amount of photosynthetically active radiation in these canopies, this is grapevines under the shade nets. There are leaves below the net, above the net, and of course exposed grapevines. Shading does reduce net carbon assimilation into the canopy, but it did not affect evapotranspiration in these canopies, nor did it affect transpiration of water vapor from the leaves. However, the amount of photosynthetically active light reaching these leaves was low. When you look at heat spikes, chronic exposure, these go hand in hand. Heat spikes, they might happen for a couple of days, but the exposure damage is chronic. So we developed this scale, examples of clusters with no damage, mild damage, moderate damage, severe damage. So moderate damage and severe damage, these are very difficult to pick with the machine. And for boutique wineries in Napa, they would be discarded. They will not be put in to the harvest stream. So based on this, we looked at the components of yield, what's marketable, what is not, based on our things. So this is percentage of clusters of damage, exposed and shaded grapevines, irrigated 40% of ET crop irrigation, exposed shaded grapevines with 80% of ET irrigation. In every case, we do not see a benefit of increasing applied water amounts to these grapevines. The main effect is removing the heat and temperature source in this case. So even if we double the irrigation amount, the cluster damage is not going to be taken care of. Of course, this reveals itself in the cluster temperatures. So we measure the cluster temperatures on northeast facing clusters, southwest facing clusters 60 days after flowering. Increasing the applied water amounts does not change a thing on the morning side or the afternoon side. What affects it is the amount of shading you can provide. Again, right around the harvest, we measured it again, morning side of the canopy, afternoon side of the canopy. Increasing the applied water amounts does not dampen or palliate a high temperature exposure in this case, but only shading can. And this, in this case, provided a 7 degrees to 8 degrees Celsius relief, regardless of irrigation amount, if you are able to shade them. Berry mass, primary metabolites, really not a whole lot to write home about in California. If you do not have a disease in this case, of course, if I irrigate them more, I'm going to have a little bit larger berry mass. But in the end, total soluble solids, they moved about like maybe a half a degree. pH was not that different, and in the end, titratable acidity was not that different. What changed in this case was we were able to document these before the heat wave and after the heat wave, and this is what happens. As I mentioned, that irrigation does not have an effect. It does not palliate the high effect of temperatures on the berries. Exposed grapes, the total anthocyanins in this case, exposed before and after, they degraded to almost by half. When I express it on a per berry basis of anthocyanins, we lost about half the anthocyanins in this case. In shaded, we do have a similar response. They do degrade, but the change in degradation is not as high, where you're losing 50%. versus 20% in this case, it is still going to be marketable. When we looked at the total flavonols, some people thought that you could use the flavonols such as quercetin, etc., to capture the damaging rays of sunlight and heat. It does not seem to help. They do degrade as well, except for one compound, which is camphorol, which we will talk about again, the biomarker for this heat damage, heat spike exposure. And this revealed to us that we can do this fairly well in California without having to hang like shade nets along the canopy. You can either design a canopy system, or you can use some sort of a different structure to protect them. So in our case, we had a 4-day heat spike that conditioned the results of the study. Stormwater potential was affected, but it did not result in a greater stomatal conductance or net carbon assimilation. Shaded with a 40% of ET crop led to better water status because it was consuming less water throughout the season. Doubling the irrigation amount did not help with anthocyanin degradation rates. Only shading is effective. Likewise, flavonol degradation did not change with doubling the irrigation amounts, and flavonols did not help to cope with high temperatures and field conditions in this case. Irrigating prior to heat spikes to increase leaf transpiration, leading to a cooling off effect at the fruit zone, similar to overhead irrigation with sprinklers or misting systems, can be looked at. However, we do not see from our data, this is the 6th year we're running these trials, that this is going to be a sustainable system for California in the end to put more water onto these grapevines. If I were to compare vertically shoot position versus sprawling systems like a single high wire, high quad, etc., we do have very few leaf layers around the fruit zone in VSP types. Misting prior to or during heat spikes may not increase transpiration or provide much beneficial cooling in this case. So you do need the leaf layers around these grapevines. Field studies are needed. This project was proposed twice, now 3 times. For some reason, funding agencies will not fund this type of work, but I'm asked to provide this information to growers every year. This is the 4th time I'm presenting this work already. Doubling irrigation had some mild and beneficial effects. Lowering berry temperature may not be justified due to logistics, and in fact, it had a little financial gain. Shading does have a positive role to retain grape berry skin flavonoids. We need to have a new research focus about the detrimental effects of extreme climatic events, such as drought and prolonged heat events that we can discuss during the panel. Continuing this work on heat damage, mitigation wine and table grapes, we're doing this work with Dios Plastics and Gym Supply out of Bakersfield. This is in its 2nd experimental year, where these films are suspended above the canopy. We did end up with less evapotranspiration, no berry color degradation, and we do have less irrigation demand in this case. So we grew these grapevines to a 7 ton to the acre yield with only 40 gallons of applied water in their first year. This is what the transmission spectra of these films do. We were very interested in this one called D5, where 20% of the near infrared spectra was removed, which meant much lower temperatures in the canopy and around the berries as well. And this is how our water footprint looked. Since they did exclude green water, they just grew with blue water with a similar yield. Control that was not covered end up with a greater water footprint than the grapevines under the cover. When I look at the relative yield, percent of control, there's not that much difference in this case. When I look at the total skin anthocyanins on a fresh mass basis for the winemakers in the crowd, or milligrams per berry to the physiologists in the crowd, control has the least amount of anthocyanins produced and retained in the berry. Whereas when I look at D1, D3, D5, they have roughly about like 40% more anthocyanin on a concentration basis or on a per berry basis. There's further information on this. I'm very well published in this manner. This paper was published in Frontiers. It's open source. I can give it to Stephanie. It's called Mitigating Heat Wave and Exposure Damage to Cabernet with Partial Shading Under True Irrigation Amounts. It's a very popular paper. So it's kind of the standard reference to go to now when we start talking about this stuff. So with that, I will yield the floor.
Fantastic. Thank you so much, Con. That was a lot of good information, and we did get some questions coming in about your presentation. So I think that we will now move into the Q&A session, and we'll go ahead and start with the questions for Con, since that is precious in our memory. And if the other presenters will turn on their video, and Con, you can just stop sharing your screen. And we'll all come back together here now. So Con, one question from Dwight was, have you worked with vine row orientation along with using modified California sprawl to try and shade the clusters?
Very good question. Yes, we did work with row orientations, and in fact, that was the main driving force in changing the row orientation the region that I work now. So when we started working with a row orientation, we immediately deduced that, of course, whatever's in the textbooks, doesn't hold true in California, because we are not growing our grapevines in New York or New Zealand. So we do not need this great exposure or heat loads in our grapevine. So if you look at the how the country was settled, especially in our newer areas such as California, we mainly follow the railroad or the main thoroughfare. So in Napa, vineyards follow the orientation of Route 29. And they were essentially parallel to the road. So in this case, southwest side of the canopy was like constantly getting burned. Then, we looked at, completely a different orientation. And then it made a lot of sense. So let me find this, and I will, can I share my screen again? So I'll share my screen again. So we did look at this with VSP and sprawling canopies, and we did determine the optimal ranges and thresholds for grapeberry solar radiation for flavonoid biosynthesis and yield in warm climates, which would be a District 11, Crush District 4, so on and so forth. So a sprawling canopy that's somewhat east-west oriented seems to be working very well, and road directions here changed very rapidly.
Con, I think you're not sharing your screen.
Oh, I am not? How do I do that? Oh, you can't see my screen now?
Yeah.
So anyways, so the paper is called Optimal Ranges and Thresholds of Grapeberry Solar Radiation. And then in this case, the question was, this is examples of clusters harvested from southwest oriented, northeast oriented, so on and so forth, inside the canopy, outside the canopy, with Cabernet Merlot, Cabernet Franc, and Petit Verdot, all the high value crops. And in this case, I mean, we can hold another session if you guys want. So this is different degrees of exposure in these different types of canopies, how these things play along. So we do have a lot of experience with that. But then again, Napa conditions are not as amicable to growing a large crop as in District 11, there might be a justification to repeat this kind of work in a Lodi region as well. But one thing that I want to show you is this canopy porosity. If you recall, I said we have the biomarker, the molecular marker for heat damage, overexposure, camphorol. This can be used as a proxy to a canopy openness. So if your camphorol percentage is in excess of 25, you're going to lose all your anthocyanins, whether it's interior of the canopy, exposed west, exposed east, or overexposed east. And this holds true for all the red varieties that we work with, except for one Italian cultivar that we do not grow, a lot of in California. But anyways, I can talk about this for hours.
So Con, that actually leads nicely into Sonia's question, which is there reason to think that one would get different results in some of the types of research you presented earlier with different cultivars or varietals, sorry.
With different varieties, yes. Yes, it would. So grapevines, wine grapes that we grow, that we can reliably sell in the open market, have different hydroxylation patterns for colors. So what's selling right now? You're selling like a Cabernet Sauvignon, right? So we're selling that. We were selling some Merlot. There's still some demand for it. But now people are trying to push like, well, how about Petit Verdot? How about this and that? They do have different hydroxylation patterns, and still the most resilient one out of these is going to be Cabernet and Merlot. Petit Verdot degrades very fast, but you don't see it because the hydroxylation pattern is a little bit different. If you're growing on Sangiovese, it's a dihydroxylated cultivar. It will not work with this. It's completely different. But majority of the cultivars that we grow for our red grapes, these things will hold true.
And we got another question for you, Con. So Jonathan wants to know, do you have any thoughts on removing leaves at pea-sized berries to promote thicker skins and more anthocyanins, and then shading from VA on?
Well, that's a common misconception. As you may or may not know, solar radiation exposure is damaging to anthocyanins. Solar radiation exposure does not promote anthocyanin production. What it promotes is a different hydroxylation pattern. So if you expose the berries to solar radiation, you will certainly degrade them, and you will end up with a much blander wine. In the new climate reality, we did look at this. We did untreated vines, leaf removal, shoot removal. You can see my screen, correct?
Yes.
And then leaf removal and shoot removal together. So untreated grapevines, anthocyanin production. You can see this is anthocyanin productivity, how much you're spending to grow 1 unit of anthocyanin per unit. Okay, untreated, it was $30 per kilo. Leaf removal, $92 per kilo. Shoot thinning, $92 kilo. Leaf removal and shoot thinning, $223 per kilo. You are going to degrade them more. Leaf removal might be recommended for cooler climates where you do need this hydroxylation pattern benefit. It does not make more anthocyanin. So I would not recommend removing leaves.
Thank you. That's it. It's good to clear up these myths when we have an audience like this. I think that's great. So Misty wants to ask all of our presenters, is anyone doing research in Amador and El Dorado counties on these topics?
On heat waves, or on grape water management?
Just in general, any of your water management strategies?
I had a research project between 2015 to 2018 on ET wine grapes grown on north-facing and south-facing slope, and that was in Amador County, was in Pilot Hills. And we, we are finishing the processing of data to publish this research. We completed the study in 2018.
Thanks, Daniele. And would you like to ask some of the questions you were posting in the chat box to the other researchers?
Oh, I have to, yeah, I have to go back and see. All right, okay. Let me see.
While you're going back and checking, and I can read them out too, no big deal. We did get some kind of logistics questions. So Misty also wanted to know, will the slides be available afterwards? And we're not sharing the slide presentations individually, but we are sharing this recording of this video. So that will be available along with all of the handouts and the maybe links to the follow-up papers that Con was talking about. Those will all be available at lodigrowers.com under the education tab. And then there's you can click on a page that is called videos, presentations, and handouts. And that's also where you can find the recordings for the first and second workshops in this series, which was a question from Mauro from Ridge.
Okay. So Stephanie, whenever you're ready, I can ask the question directly to the speakers, the question that I put in the chat.
Yeah, that would be great. That'd be great.
All right. So one question to Mark Battany, if he's online and connected. I was asking whether Mark can clarify to the audience if that relation between NDVI and crop coefficient or water use was evaluated and validated for wine grapes in arid and semi-arid climate like the one in California, because this is pretty crucial for the application and use of IRRISAP model. I know it was developed for, the model was developed mainly for field crops, so I'm just curious whether some kind of evaluation of that relationship between NDVI and crop coefficient was somehow validated for wine grapes.
It doesn't look like we still have Mark anymore. Great question.
So, yeah, so I think Mark texted me that is getting on and off because his connection is not reliable today. There's a question for Tapan. Your slide about temperature in Lodi shows a sharp increasing trend. Does this mean that water needs will be higher, or it also means that the grapes growth season will be shorter, so the seasonal water needs will not change much?
Okay, so it's just sort of a little bit complicated. Yes, so temperature increases will definitely have impact, because it's part of the ET equation, that if you have temperature increases that do influence ET somewhat. How does that affect the growing season? Well, if you consider no adaptation, that definitely has an impact on the growing season, right? And so, Con mentioned about the shadings and other effects. And so if you do include those, and that influences the growing season, but temperature itself can have the phenology shift happening, but that comes with effects on the quality as well as the yield itself. And so so what these kind of slides do show is that given this trend, we need to take some sort of adaptation into practice. And so I can't give the direct answer to that, because if it is influencing the growing season, if it is shrinking, that also affects the yield and the quality. So sort of takes into counter effect.
All right. There's a follow-up question, Taban, and this is about CO2, because the prediction for climate variability and climate change show an increase in concentration of CO2. And would this mean that wine grape will transpire less because of the higher concentration of CO2 in the air?
Well, CO2, just in a general sense, CO2 has different effects on different crops. CO2 in general increases the photosynthesis process. And so I don't know much about how it affects the wine grapes. Maybe Khan and Mark Batney or Danielle might have more idea. But in general, if you have increase in the CO2, that could affect their ripening process. So maybe it can ripe sooner, but that does affect the quality aspect as well. So I don't know whether it's like from variety to variety, it's a difference, but maybe Khan can mention more about that.
I mean, if there's an increased CO2 and more water available in the soil profile, ripening rate is faster. So you're going to accumulate more bricks per day, so you can possibly ripen faster. But then again, it depends on your water supply. If you're able to supply these grapevines with 2 acre-foot of water, let's say under if carbon dioxide magically doubled, you would get it faster. But it's not doubling at this point. But as an anecdote, when I started my career, the amount of CO2 in the atmosphere was around 340, 350 parts per million in the ambient. Right now, it's around 400. Yeah, so it's a 50 parts per million increase from 1997 to 2020. So it's a big jump. So it's moving pretty rapidly.
Yeah, and this is more of an interactive effect as well. I mean, if you have CO2 increase and if you have enough water, that could potentially have a positive impact. But if not, then it could have a detrimental effect as well.
Yeah, there's a question to Khan. According to your experience, is micro irrigation the adequate irrigation method to prevent or minimize or mitigate heat damage, or wine grape growers should consider having dual irrigation system in their vineyard? So drip and flood, drip and micro sprinkler, drip and sprayer, because it looks like from your presentation the direct effect of water is not there, but the shading effect is important. So maybe growers can manage water to create additional canopy to shade grapes.
Well, we do that very well with our modified California sprawl. However, the damaging solar radiation is not visible. So you need to remove this source of heat. So if you can, sprinkle the grapes, with an impact sprayer, impact sprinkler, for example. But then, how much water do you have to put on? That would be the question. And the drip irrigation or micro irrigation we did, it's nothing new. Mark Cleaver did this work 40 years ago. So a lot of research is research, I think. But shading, creating a nice environment around the canopy of the fruit is going to be more important. But if you look at impact sprinklers, 2 hours is equivalent to about a quarter of an acre-inch in this case. So I don't know where we're going to get this water to supply this volume to cool these grapevines down. So building different canopies, different trellises, or this overhead shading is like a boon, because we reduced that evapotranspiration by 30%. So these seem like some out of the box thinking in this case, because it's a new reality that I'm having a tough time wrapping my head around, because my parents are raisin growers, and they're dealing with the stuff like with grapevines, failing in the field on a 5 BB rootstock now. So.
Okay.
Yeah. Con, there's another question from the audience for you from Charlie. He says, would you recommend for the Delta region Pinot Noir to not pull leaves to have the highest anthocyanins concentration at harvest?
Why would you remove leaves in a Pinot Noir? First of all, Pinot Noir has does not have a acylation, so it just has the 5 base color compounds. So increasing a light amount to a Pinot Noir is just going to degrade this. So yeah, I would not remove it. So the most amount of light you would need around the cluster is right around like 20%. After that, it becomes damaging. So there's no reason to expose them.
Thank you. Daniele, did you have any other questions?
Oh yeah, there's a question to Marnus and Dirk. So a lot of vineyards were somehow established during time when soil variability was either not easy to detect or was somehow overlooked. Now, if a system is designed to apply almost similar amount of water for the different across the vineyard, but there is a soil variability, would a grower be able to adjust for this soil variability based on the frequency and timing, only having one block or one irrigation sector, or what will be another management strategy to minimize the difference in crop growth and the production?
Yeah, good question. So if it depends on what the problem is, that's the short answer. The long answer is, let's say you have a patch that is running too dry. So then you would, for that section, you would have to try and improve the water holding capacity of that soil, or at least reduce evaporation. So a strategy would be to either, if you have access to organic material, to preferentially mulch that area. That's one strategy. Do not do it for everything else, because all you want to do is preserve the amount of water that's in that area. You can do that. Some guys use quite effectively weed mats to stop the burn off, and again, about 30%. You save about 30% of water generally is what we find by doing that. You don't have to give as much. So what you want to do is just reduce that stress. Ideally, if you have an irrigation guy that's near to you, they can maybe, if you're running drip, for example, and it's pressure controlled drip, but by the sounds of it, it sounds like it might be an old system. But if it's a new system, you can adjust. You can maybe add a dripper line to make it a double drip system, or change your rate of delivery in that area. So, but the short answer is it depends what the problem is. So we can come and have a look to see exactly what the issue is, what's causing it, and then you have to make management plans according to that.
Okay, thank you so much.
I think if I can just make one comment there, is one of the services that we offer is soil classification. And during our soil classification and the mapping of these soils, we are able to determine these leaching denitrification zones and effective plant available water holding capacity in the soils. And I think something that's been very useful for even existing vineyards and orchards is where we were able to identify the most ideal probe position where to do the installation of a soil moisture probe if you can irrigate according to that probe. And that's been very helpful in existing systems. So we have a better representative area of where to place that actual probe. And then obviously in any redevelopment and new developments, we actually consult with major irrigation companies right now, where we provide them with an irrigation zoning map, and then they start just do the irrigation design according to the data maps that we supply them, based on the data from the soil classification that we've got during our investigation.
Okay. And there's a question for Joel Kimmelshoe. Joel, the slide that you presented are mainly related to a service for land use mapping, but also for ET quantification. Can you give the audience an idea of the cost of the service for the ET measurement and quantification, and whether there is a service provided by your company for shorter time steps, so either biweekly ET that can help a grower association to schedule irrigation, to get some information for irrigation scheduling?
Yeah, can you hear me okay?
Yes.
Okay, thanks. To answer the last question first, we deliver our data. We work in very large landscapes and we deliver the data. It takes us about 25 days after the end of the prior month to get all the data from the ground truthing stations and QA/QC that and then run the analysis for that month. So unfortunately, that's about as quick at this point that we can do that. So I think probably the source of that question may be, can we use this information for kind of day-to-day irrigation scheduling? So you can use it for irrigation scheduling, but it wouldn't be as timely as a day-to-day time step. It would be month to month. And many of the GSAs that we work with or irrigation districts are transitioning that information to their growers through a web platform or online in their web page or whatever. Unfortunately, it's harder to do it the way we do it with stations and ground truthing like we do. It takes more time, but the objective is to try to reduce the variability around the actual value of ET. The cost depends on the complexity of the landscape. So and how big the area is and how big the fields are or how little the fields are, and how many crops are in the area. It can range from all of the costs are below $1 per acre per year. So you're in the cents per acre per year time frame.
Okay. I have a question.
I think we have to close it off, Daniele, because we're at time.
All right.
Thank you for adding all those additional questions at the end there for us. Really appreciate it. And you did such a fabulous job of assembling this great team of experts for us. Thanks to everyone who presented and who attended. I think this was very valuable to our industry, really timely, and we can't thank you enough for your time today. The recording will be posted online, and hope everyone goes and has some hydration for themselves as well today. And we look forward to seeing you again in the future at another workshop. Thank you very much, everyone.
Thank you.
Thank you.
Joel, do you have a few minutes after?
Sure. You want to give me a call?
I'm just going to stop recording, and then we can just talk really quickly now if you want. If I can figure out the right button here.